Hello everyone, my name's Gemma Sherwood and I'm here to talk to you about my role as a geologist on the construction of Hinkley Point C. Now I was seconded to Hinkley Point C from Atkins into NNB, which stands for New Nuclear Build and part of EDF Energy, in October 2016, mainly working on the enabling works. Now I was brought in to provide technical support and also site surveillance as a field geologist. Now, on this project, NNB are the client and principal contractor, and we're supervising the earthwork contractor who are Kiabam joint venture. Now, my main motivation for joining this project was because I wanted to gain more construction experience, but also because it's a fantastic project to work on, and particularly of this scale and complexity. So, Hinkley Point C is the first of its type to be built in the UK. It's a European pressurized water reactor, or an EPR, and the two are going to be built. As I said, first of its kind in the UK and the first new nuclear build in 25 years in the UK. Costing almost £20 billion, it will power over 6 million homes. Hinkley Point C is located just outside of Bridgewater on the Bristol Channel. East of the site is Hinkley Point A, which is a nuclear power station currently being decommissioned by Magnox. And further east is Hinkley Point B, which is an operational nuclear power station owned by EDF Energy. This is now a photograph of the site. I've been told that it's a mile square, or 400 acres, or 300 football pitches in size. The site itself is split into two. We've got the northern half, which is the main construction area, and where the two nuclear reactors will be sited. And we've got the southern part, which is actually a valley called the Holford Valley, and it's separated by a historic green lane running east-west. The whole site is a cut and fill exercise, so all of the material removed from the northern part of the site is going to be reprocessed and either reused as construction fill or going to be reused to backfill the Holford Valley in the south. This means that no material was removed from site, which makes it cost-effective and environmentally friendly. So the geology and depositional history of Hinkley Point C is relatively simple. The rocks found on site were deposited on the southern margin of the Bristol Channel Basin and are Permo-Jurassic to Jurassic in age. They were formed when UK was part of Pangaea, and the southern part of England was located close to the geographical position similar to the Sahara Desert. The geological sequence is a change from terrestrial to fully marine conditions, and this is caused by sea level rise and the slow inundation of the basin due to crustal extension. The oldest rocks that we have on site are from the Messier mudstone group. They're Triassic in age. The red mudstones were deposited in the interior of Pangaea and from wind-blown deposits and from hypersaline mudflat environments. Now, they're rarely seen on site. We've actually only encountered them when we've excavated at the bottom of the Holford Valley in the south. These are overlined by the Triassic rocks of the Blue Anchor Formation, which are dolomitic siltstones, and were deposited with evaporite rich. These represent tidal salt marsh deposits. And then with rising sea level, we move sharply into the Penarth group and by this very distinctive Westbury Formation, which was deposited in anoxic, organic-rich swamp environments and formed these very distinct black shales. We then move into the intertidal zone of the Lilstock Formation, shallow marine deposits, and then moving further into the Blue Lias Formation, where we're in fully marine conditions, and we get a nice interbedded mudstone and limestone. So this is the structural geology of the northern part of the sites. This is everything north of the Green Lane. The Blue Lias Formation in this map has been broken down into biozones. So that's the yellow, pink, blue, and green. And these biozones are marked by biomarkers, which are ammonites. And this is very useful on site because it means we know exactly where we are in the sequence when we're excavating. The faults are trending northwest, southeast, and east-west, and they were developed during the Variscan orogeny. These are normal faults and formed by basin evolution and rifting, and they were later reactivated in the tertiary. Now, the inferred fault locations, which were determined during ground investigations, have actually proven to be relatively accurate during construction. However, this map can be quite misleading because we do get a variety of extents of faulting, from minor offset of limestone beds to large-scale faults with major offsets, intense weathering, and deformation. Other structural geology, as you can see from this map, is that there's an anticline trending east-west, which has been later offset by faulting, and away from the anticline, all of the beds are quite consistent, all dipping towards the north by about 6 to 12 degrees. And this is an excavation model of the 2 nuclear reactors, the deepest of which is about 33 meters in the northern part of the site. And this is the geology that we're encountering, or that has been encountered. As you can see, most of it is the blue lias formation, which is fantastic, because the blue lias formation is actually the best material that we have on site for material reuse and for its in situ engineering properties. However, as you might be able to see from the model, in the southern part of the nuclear reactors and in the southern galleries, we're also encountering some of the minor lithologies, including the Glossop Formation, Westbury, and the Blue Anchor Formation. And these have their own engineering geology challenges, which I'll go through in a second. So what does my role entail, and what do I do day to day? Well, I'm responsible for ensuring that the client specification is followed by the contractor. I do this by by undertaking site surveillance and by supervising activities such as ground investigations, geological logging, mapping of horizontal and vertical formations, and material assessment. Now, the ground conditions do vary across the site, and I'm responsible for ensuring or for assessing whether the ground conditions encountered are as expected and whether or not they conform with design assumptions. I then sign off quality inspection records in the field and then approve and check geological reports back in the office. So where construction processes aren't followed, I raise non-conformance report requests, and I also follow these up with learning reports from lessons learned and safety observations. So this could be a typical day for me. In this photo, we have AECOM geologists logging a vertical face. In parallel with the AECOM geologists, who are the contractor slope designers, I'll also undertake an independent assessment and record features such as rock strength, geology, joint sets, assess potential kinematic failures, and also assess the geological strength index. I then compare my results with those from AECOM while in the field, and then also check their report when we get back to the office. But more often than not, this is actually my day at the moment. This is a horizontal formation mapping. And the horizontal formations are the foundations of the nuclear power station. And unlike the vertical slopes, which are actually temporary, the horizontal formations require lifetime records and directly affect nuclear safety. So I supervise and undertake independent assessment of the formation mapping, which is in this case undertaken by the key-bound geologists. So as I said previously, the geology of Hinkley is relatively simple. However, the lithologies that we're working with do have their own engineering geology challenges. For example, in the south of the site, along the Holford Valley, we did encounter peat. Now, this was completely unexpected and directly affected the methodology and design for the backfill of the valley. It also caused instability of our spoil heaps, which we're temporarily storing on the south of the site. And although spoil heaps are temporary features, they do have implications for health and safety and also for the temporary works design. More importantly, and some of our biggest challenges we've had recently are sulfates in the Blue Anchor Formation. Now, we knew that sulfates were present in the Blue Anchor Formation, not only from our ground investigation, but from the depositional history of it. However, the ground investigation revealed that we weren't supposed to encounter sulfates, or in this case gypsum, until about 5 meters below the top of the formation. This was perfectly adequate for our construction because we weren't going to go that deep. However, that's not actually what we found when we started constructing. And this had long-term and short-term effects on our construction. Short-term effects are the dewatering. We can't dewater in the Blue Anchor Formation for risk of causing the gypsum to dissolve and create dissolution features. And we need dry excavations in order to carry on excavating. Long-term effects are that there's a potential for voiding-induced settlement to occur, and particularly beneath nuclear-related buildings. Pyrite, we have pyrite in our Blue Lias Formation, Westbury, and Glossop Formation. And as we know, pyrite causes thaumasite attack on our concrete. Well, we've got a lot of concrete on site, and so in order to reuse these materials, one of the easiest ways that we've found to remove the pyrite is to stockpile it and let it naturally weather out. However, this has its own implications because, as you can see from the photograph, particularly Westbury, weathers incredibly quickly and then changes its material properties for reuse. So this has been an issue as well. And finally, our faults. As I showed you earlier, we have a fault map. We have a number of faults crossing the site. And this has particularly been challenging in our excavations. So as you know, faults cause slope instability, such as in this top photograph in the interior of our galleries where we had a global instability. So where faults are encountered, we've had to take additional steps to reduce instability and increase the factor of safety of them. And we're taking measures such as using ground nails, grouting, ground anchors where required, and also drainage to reduce the pressure behind the face. We're also monitoring the slopes using inclinometers and survey prisms. Faulting is also directly affecting our hydrogeology. So the limestone beds have higher permeability than the mudstone because of discontinuities. However, faulting causes offsetting of the limestone beds. Where it causes offsetting, it disrupts water movement, and this means that as we're dewatering, we're actually causing perched water tables to develop, and this directly affects our excavations. So there are a number of lessons that can be learnt from Hinkley Point A, which was constructed in 1957 and is directly adjacent to our site. One of these is asbestos. When Hinkley Point A was being constructed, the construction area was actually where Hinkley Point C is currently sited. When the workshops and the materials were then demolished, high amounts of asbestos contaminated the ground, and this had to be remediated by hydrock in a series of phases. We've also had hydrocarbons from fuel spills and where fuel was stored on the site. This wasn't discovered in our early ground investigations. It was actually only discovered when we did dewatering earlier this year. But what we can definitely learn from Hinkley Point A is from these amazing photographs that we have of the early construction. So this is a photograph of the heat sink. And apart from the lack of PPE, a three-piece suit and a flat cap being deemed suitable protection in those days, there's a lot of information that we can get from these photographs. So, for example, the geology. We know we were in the Blue Lice Formation because we can see the interbedded mudstones and limestones. Hydrogeology, well, we can see that the faces are soaking and that they're standing in ponds of water at the base. And if you study it closely, it looks like they're using rudimentary pumps to remove the water, which indicates they were definitely having issues with dewatering and dry excavations as they were lowering the lifts. And the most striking thing about these photographs is the stability of the faces. This excavation must be between 15 to 20 meters high. And as you can see, there's no instability of the faces. There's no movement or dislodgement of the upper layers. Now, this is very different from the approach that we're taking today. We're using smaller lifts to ensure stability of the faces. We're using spray concrete to make sure that nothing falls off the faces in the meantime. And we're using ground anchors and ground nails, as well as drainage. And this ensures a higher factor of safety for the slopes, but also because we're working to Eurocode 7. And also, unlike back in 1957, we're actually siting large cranes at the crest of these slopes, which are going to lift precast parts of the nuclear power station into place. So we'll be having higher loads and will require additional support. And again, another photograph from 1957. This is actually the reactor building. And I just wanted to point out that the internal corners. So where the beds are dipping towards the north, we have, where they're dipping into the excavation, we have dislodgement of the limestone blocks, and also you can see a kinematic failure where the adversely dipping joints. We knew this part of the study and of the design for the slopes, and yet as soon as we started excavating in the galleries, we found exactly the same thing happening, and this is an internal corner from one of our early excavations. This has now been, or steps have been taken now to prevent this, including stitch drilling and vertical dowels. So to conclude, I just want to share with you some of the lessons that I've learned from Hinkley Point C and my experience on site. The geology on any site can be challenging, and it's very important as part of the design and the construction, even if the initial geology appears to be relatively simple. My role as a geologist on Hinkley Point C has meant that I have had a lot of responsibility assessing and accepting ground conditions, as well as approving lifetime records for nuclear power station. Technical assurance on behalf of the client is essential. We almost act as a buffer sometimes between pressures of the program, cost, but also the requirement for the works to be undertaken to a high quality and adhere to design requirements. So for those of you here that are early in your career, my message to you would be get out on site as much as possible. See the ground that you're looking at and what you're writing reports about, but also learn from your colleagues and take this opportunity to learn from other disciplines. And from those of you here that are later in your careers, more experienced people here, my message to you would be that we need to make sure that we're training and mentoring our next generation of geologists and engineering geologists, because they're going to be the future of our new nuclear builds. Thank you.